Hello, everyone. Good afternoon, I guess. And again, thank you to the organizers for having me. I'm going to share my screen now. All right, great. Thanks for your patience. And so I'm going to cover an overview of enterprise knowledge graphs. And I just want to state before I get started that this is going to be conceptual. It doesn't reflect what we are actually doing or not doing at Wells Fargo Bank. So I wanted to put that disclaimer out first. So what I'm going to cover today is the essence of what knowledge graph is as a paradigm shift for enterprise data. Then going to cover a bit of the architecture of a knowledge graph environment, and then essentially a set of use cases as to when do we want to use knowledge graph technology. So just to get started, companies have invested massive amounts of capital in legacy data technologies to meet their data challenges. But we're in the we're now entering the third decade of the 21st century, and we need something new. So why would we need something new? So looking at the past number of years with relational technology, we found that as a result of highly siloed organizations, there, as well as many dictionaries and glossaries that are very incongruent, and the massive explosion of data in the enterprise, an aging data paradigm is really not well equipped to support the exploding challenges of data today. This paradigm, a relational model, is now 50 years old, has resulted in very incongruent data models and massive proliferation of bespoke labels for columns, insufficient metadata, and many different kinds of siloed data platforms, from glossary platforms to metadata platforms to the actual relational database platforms to other kinds of data technologies. It's highly siloed. This has resulted in the current state of very high costs to manage data, inefficiencies, errors, compliance problems, vulnerabilities and risk management, and of course, it leads to limited abilities to better serve customers. Knowledge graph technology, which I'm going to further introduce to you, can offer transformational improvements. So first, what is a conceptual knowledge graph? Well, what that is essentially a very rich model that represents knowledge and is able to describe and express the meaning of concepts. And it does this by using nodes or which reflect concepts or entities that link to other nodes that reflect concepts and entities in a network pattern. And these relationships between these nodes, or what we call edges, are intelligent. They specify a very rich relationships. And this can all be understood in the context of what we call this conceptual model. We call it an ontology. So we'll have a first-class object, as we'll call customer. It's a node. It's linked to another node, which we can call a checking account, and another node, which is a credit card account. The label for that, which we call the predicate, has account. So we could look at this, we call it a triple, the pattern of a subject predicate object, which is a way by which we describe concepts. And subject predicate object, as you can see, is already linguistically aligned with how we think and speak. There's more intelligence here where we could say these two nodes, checking and credit card account, are kinds of accounts. And these checking and credit card accounts also have attributes, such as they may have transactions, which link to a transaction concept. And these transaction concepts have related relationships or concepts to a monetary value or a merchant, where the transaction relationship is purchase from merchant or purchase amount, some monetary value. So this is a very high-level overview of what we would call an ontology, which can provide a common language for understanding. Now, an operational knowledge graph is a network of connected data using this ontology. So the model that we just saw before is a conceptual model, could be represented with real data. And so the credit card account may have multiple transactions, which are realized by having other nodes connected with edges to that node, and so on and so forth in a network pattern. So you could see a fan out of data that's related to the common model. So you get a very big picture of all the relationships between the data. So we might look to see information associated with a given merchant, and you could traverse the pathways or these edges to locate all the data that's been materialized in the graph that's associated with a merchant. It's very similar to having many joins over relational tables. The challenge with that is that you never know in a relational database where all the links are. With a knowledge graph, it's much easier to traverse the pathways that are already put down as railroad tracks to the data. Likewise, we have many siloed environments or lines of businesses with a knowledge graph, or I would call a federated knowledge graph. You may have information in different lines of businesses, like a debit card line of business or a commercial card line of business or a credit card line of business. And with the knowledge graph capability, we're able to use the same common language to federate across all of these different remote or distributed stores, because we follow a common language based on the protocol of the web. So the semantic web is a way of extending the web of linked pages and the web of to become the web of linked data. So what is the knowledge graph trajectory? So we move up a scale of things that humans understand to where machines understand. And this also aligns with the expressivity of the information model. The more expressive your information model, the more robust it will be for you to draw connections between information. So again, back to 1970, we start with the relational model where we have tables and columns. Tables represent entities and columns represent attributes. And you have to know the physical model of the table in order to figure out what you're going to connect. As we move further into now the 21st century, with the advent of knowledge graphs, we'll call knowledge graph 1.0, with the creation of the semantic web language stack, which is a global standard. We could call this an aspect of knowledge representation and reasoning. Again, we have concepts represented as nodes and relationships to other concepts as based on these edges. We then move up the stack to what we'll call knowledge graph 2.0, which now begins to converge with machine learning with ontologies, where we could now move from things, which Google termed things not strings, to predicted things, where we could use machine learning to predict various new classifications, new inferences that we could link back into the knowledge graph. And it's much easier to link this information into a knowledge graph because of these first-class objects, these nodes, than in a relational table. But that's not where we stop. We can move up to knowledge graph 3.0, which now takes these nodes and edges, and it uses deep learning plus machine learning to predict points in a low-dimensional vector space model that are semantically related to the nodes and the edges in the knowledge graph, so that we can end up with very highly scalable analytics that align very much with the actual nodes and edges in the graph, where we can do some very highly scalable analytics. So knowledge graph positions us for many new strategic capabilities with enterprise data. We have a common semantic model using the ontologies and using the semantic web language stack language RDF OWL to create an enterprise standard. We can also leverage another standard called Shackle, which stands for Shapes Constraint Language, which provides data quality rules that leverage the same common semantic model. So we have alignment with data validation with the model. We can also build a layer of knowledge over our physical data assets using the knowledge graph. So we have intelligence over our legacy data assets. And then we can leverage the knowledge graph to provide a better way to link and integrate data because of the harmonization to the common language. And this creates a very powerful next step, next generation strategic opportunity for enterprises. The result of this, in contrast to legacy technologies, is a significant reduction in errors and costs, improved and increased efficiencies, improved insights, faster time to knowledge, better ways to mitigate risk, better ways to serve customers, and better regulatory compliance. So, quick overview of a knowledge graph architecture or environment starts with our ontologies or enterprise ontologies, which we take from a conceptual view to an operational view that can be queried for understanding. The major use case that we'll talk about first is this data catalog capability, where we can use the layer of knowledge from the knowledge graph to facilitate insights into our legacy data sources, our data lakes, by creating linkages or mappings between the concepts and the physical data elements, the columns and tables and databases. So this leverages the ontologies as well as machine learning in order to scale these mappings. We also then have a semantic curation process that allows us to leverage the insights and the understanding of the physical data assets through the knowledge graph to ingest data and then to harmonize it, transform it into the proper knowledge graph format, and then materialize it into an operational knowledge graph over here so that we can query it. And we can also leverage machine learning against the operational knowledge graph to better connect the dots by using link prediction and entity resolution techniques, classification techniques, and then ultimately these encodings that support what we call graph representation learning or knowledge graph embeddings. And we can create a consumption layer where the operational knowledge graph can, on demand, have content extracted into spreadsheets or in a JSON LD format or into documents like PDFs, into tables, or into other more simpler graph structures, more homogeneous graphs for more simpler graph analytics and more refined, simpler use cases, as well as into this graph and embedding space where people can consume it, data scientists, business intelligence, and data analysts, as well as it can respond to service requests or APIs or microservices from applications to retrieve knowledge from the operational knowledge graphs or these extracts from that knowledge graph, which we could call knowledge as a service, which uses protocols like JSON LD or GraphQL. So the question here is, when should we invest in knowledge graph technology over conventional methods? While I was talking about a lot of the limitations of legacy technology, I want to be very clear that relational technology is going to be here for many, many years to come. In fact, many use cases will demand a relational solution by virtue of the necessities of the use case. However, now with the advent of knowledge graph, which is ready for prime time, it's ready, it's industrial strength, we have additional tools to basically add to our tool chest to support certain use cases that a knowledge graph is best equipped for. And I'm going to go into what some of these are. So we want to use an EKG or an enterprise knowledge graph when we want better capabilities to represent enterprise glossary definitions and concepts. So for example, a standard glossary term in a company would be first would have a term label, in this case account, and a definition. That's pretty much it. That's what the enterprise struggles to come up with alignment on. And this has some real limitations. First of all, it's nothing that could be easily operational. Contrast that with where knowledge graphs are going, where the knowledge graph will eventually become the system of record for enterprise definitions and dictionaries. So instead of a label with a definition only, we'll have an entity or a concept for that particular item, in this case, a node called account. It'll also have the same definition, but in addition to it, it's going to have the related concepts. So you can think of account in a more holistic manner in a knowledge graph because it provides the related concepts that provide the full context of understanding of that account. Think of it as moving from a single dimension to a multidimensional view of information where we could see the account has relationships to other first-class objects that better describe the account. And so looking at these clusters of objects, you have a much better understanding of account than simply looking at a definition. And this provides the basis for a common language for the enterprise for standardization and reusability, as well as it provides the opportunity to operationalize this conceptual view so that we could traverse it for many other use cases. And this can also be operationalized for visualization. So this is something that triggers the notion of graph visualization, visualizing a graph. We also would use an enterprise knowledge graph when we want a better data catalog capability. So a user might ask questions, where are credit card account identifiers across different systems? What is the information security classification of a credit card account identifier? In a legacy world, something we're very familiar with, we'll have many columns and tables with all different bespoke labels. In certain cases, we may have two columns together. In this case, for a credit card identifier, it would be an account number plus an account type equals CR. How do we make sense of this when there are dozens and dozens or hundreds of these bespoke columns? Metadata repositories, you almost have to know what you're looking for in order to look for it because they don't give you that full context other than maybe some string search and string matching capabilities. Or for the classification, you'll need security policies to understand what is the information security classification of a credit card number, but it's not easily automatable in its current form. So the big gap with legacy technology is there's no common model over the technical metadata. Fast forward to what we would call a semantic data catalog, it's really a knowledge graph plus metadata. So we'll have the concept of an account identifier and the concept of a card account identifier, which is a kind of an account identifier. We'll have something more specialized like a credit card account identifier, which is a kind of a card account and an account identifier. Think of it as sets, things in bigger and bigger sets. So the concept then can be mapped using a variety of techniques to the physical data elements, the metadata essentially. So we can then ask the question, where are the credit card account identifiers across the different legacy systems? It's easy, we just query the knowledge graph for a credit card account identifier and it links to all the different columns and tables that represent it. Also, we might ask, what is the information security classification of a credit card account identifier? Because we have the notion of a concept associated with another concept, we could say an account identifier has an information security classification of confidential. Therefore, all things that are account identifiers inherit that relationship. So we ask the credit card account identifier, what's your security classification? And the answer is confidential. Therefore, all elements that are mapped to it are confidential, and this can be queried. So essentially, concepts describe columns. We want to use an EKG when we want better data quality rules. So I'm introducing here this notion of a new standard, the shapes constraint language, where it's a knowledge graph in its own right, and it basically describes the rules using a knowledge graph itself that basically states that if you're a person and you have a tax ID number, you can only have a maximum of one. It must be a string, and it must follow a pattern of 3-2-4. So when we actually have data ingested into the knowledge graph, Bob is a type of person. Bob has tax ID number 12345 ABC. Well, we'll know something is wrong with that by executing this shackle execution capability, which will automatically detect that this value doesn't match the pattern, and it will basically generate a report that describes why it's non-conformant. And this can then be identified in a semantic catalog where we could query social security numbers or tax ID numbers associated with people linked to the tax ID column in the customer table in the marketing database. We may then see the results that this particular data element from a particular lineage may have a high number of errors, so we get a sense of data quality. We may also want to use an enterprise knowledge graph to link information from multiple different data sources. And so each of these different silos will have an ontology and an operational knowledge graph model. And following a semantic harmonization process, we can integrate all of this together, link, federate, harmonize the information so that we can query across all of these different data sources through the knowledge graph and identify insights, particularly holistic view of customer information we may not have seen before. So again, this linkage is done because of a standardized web addressable identifier for each of these nodes and entities and relationships. We want to use an EKG when the basic use case reflects a networked organization of data, customer 360, predicting entity resolutions, next best products, etc. Payments networks for money laundering and fraud, trading, counterparty risk. All of these relate to networks of information. Technology asset management, where we have a very, very complex network of physical assets that are used to power the enterprise. This is all very low-hanging fruit for knowledge graphs. We want to use an EKG, again, when we want to harmonize disparate data. So in this example, we have two renditions of a customer table, one spelled out as customer, one as cust, with different data content, different labels for the same columns that really ultimately mean the same. The semantic harmonization process will use techniques to ingest the data from the basic physical data source and then transform it into a knowledge graph representation where we have these first-class objects that, again, reflect a common language, where we could create this thing called a customer, which has an identifier whose identity, customer's identity is a person, and it'll have different attributes that will link to this object, and it'll reside at a residential address, again, a first-class object across the enterprise spectrum, and a date of birth. These are all objects with labeled edges tied to other objects. Because these are first-class objects, they're persistent, and these will have the ability where we could query the object for the residential address and ask it who else resides at your location, because it's this, again, persistent smart object, as well as are there any loans against this particular residential address. So the the knowledge graph is very smart because it allows you to focus on a particular named entity and query it for its relationships. Likewise, you could query a date. A date could be persistent across the enterprise and ask the date for all of the transactions where it has occurred. You could use an EKG for better queries across a taxonomy, where at the lowest level, you may have a common standard representation for a charge-off across different lines of businesses. The language is always the same, charge-off. And these can be modeled in a very expressive taxonomy where home and auto loan accounts are modeled as kinds of loan accounts, and retail credit card and business credit card accounts are modeled as kinds of credit card accounts. As a result of reusability and standardization, a very large percentage of each of these different accounts are all common at the loan account level. You think of it as commonality and variability. About 90% of a credit card account or a loan account uses the same semantic terminology. And these can then be further linked at a very high level of abstraction, lines and loans, where there is again a common set of relationships. So the beauty of this model is that it has built-in taxonomy into the framework of the knowledge graph. And we might ask at the very highest level of lines and loans accounts, which will also have the attribute charge-off. You can ask it at this level for all of the portfolios that are part of the set of line and loan accounts, and for all of the line of business accounts, what are the total aggregate charge-offs across these sets of portfolios? You can do this in one simple query, whether it's over a consolidated knowledge graph or whether it's over a federated knowledge graph, and it will roll it all the way up to the top and provide an answer. And this could be a click and a very easy development where the CFO can get an answer immediately without incurring a massive development effort that we incur today, because so much effort and cost is built in translating up at all these different levels what the different bespoke label represents. And we could eliminate that essentially when we have this enterprise knowledge graph capability. Few other use cases when we consume highly variable and highly dynamically changing data into the knowledge graph, where, for example, we have ways of obtaining all kinds of variable information about a person. This can easily be linked to the person object from all of these other sources. This can be done first very quickly by having ontologists do rapid modeling and deployment, where we could say it's human engineered. There are no DBAs in a knowledge graph. There's no physical model. So you add the concept and it can be easily, quickly operationalized with the right governance. And you can have very rapid turnaround to ingest new data without incurring the weeks or months of delay with conventional technologies. Or as we move forward with machine learning, many of these new data relationships can be automatically learned through machine learning techniques called ontology learning and knowledge extraction methods, where it could be machine populated, typically with a human in the loop to validate it, but we're moving in this direction. Another one is when we want to discover new relationships. So here we have a, customer B, person B, and they have addresses, names, and other relationships. We may ask questions about this by running what's called a random walk against the nodes in the graph. And what happens is we can execute various algorithms like link prediction, entity recognition, entity classification, entity resolution, where as a result of these algorithms, we could infer a whole new node that can link these different entities, person A and person B. And based on the outcome of the prediction, we may infer person A and person B exist in the same social relation. Or person A and person B exist in the same household, or person A and person B are actually in the same family relation, or person A and person B are actually equivalent, they're the same person. Therefore, customer A and customer B should be linked together. So there are many other ways of using knowledge graphs with, in this example, we can capture text and parse it into its subcomponents and translate this text. I'm planning to buy a truck to expand my construction business into the nodes and edges in a knowledge graph that reflect meaningful information. And this can then be further queried through graph representation learning, where we can do very fast translations of the nodes and edges in the knowledge graph to basically this whole new notion of what we call a vector space model, which are numbers. And these numbers create digital fingerprints for the concepts and the relationships in the knowledge graph that allows machine learning algorithms to very rapidly iterate through these points in a vector space model to make these predictions, like understanding the intent was to purchase a truck, the context is business expansion, and the actions are to recommend an auto loan or as well as to increase the credit line. So I wanted to tie this up to Knowledge Graph 3.0, and we've covered all the various aspects of Knowledge Graph. And with that, I conclude my presentation. Thank you very much for your time.